So that's a little preview of some streamlines. And now we're going to talk about an algorithm for the placement of streamlines. How do you place them? If you're on the bridge, you need to visualize the flow. It would be nice to have some sort of a placement strategy that covered the whole surface of the river, if you want to visualize all the properties of the river, at least at the surface. So this is what it looks like if you divide the space up into a Cartesian grid and place a seed at the center of every grid cell. This is what it looks like. Firstly, it is ugly. It's just not nice to look at. Anybody notice any other problems there? Any disadvantages with the left image?
So there are some undersampled and oversampled areas?
Yes, very good. You're going to do well on the test, I bet. That's my psychic powers telling me, giving me signals. So yeah, there's lots of overlapping streamlines. That's also called oversampling or redundant sampling. That's not nice. And there are gaps too, right? Gaps. So that's also called undersampling. Space is missing. That's Cartesian grid, the naive. If I asked you to implement a streamline seeding algorithm, this is the one you would choose first, because it's easy and it somehow makes some sense. But this is the result you would get. You'd find out that it's ugly, and it has some drawbacks, oversampling and undersampling. This is a different streamline seeding algorithm. So it looks much nicer, and it tries to sample the vector field in a more even way, more evenly distributed way. So the idea is that you don't miss any features, and you don't oversample, and you don't miss any features. This is not the world's most exciting flow-based example, the vector field. Like what we saw in the video is more exciting. That's why I showed it. But this is the idea. So how do we do that? How do we accomplish that image on the right? The idea is that in this example, you have a Cartesian grid, and you just have a seed at the center of every grid cell, and you just trace the streamlines, and you ignore what's happening around you. It's a brute force kind of approach. These streamlines don't know about each other. They have no awareness of each other. The essence of this one is that streamlines, when they are traced, they are aware of other streamlines. That's the essence. Like if you want to get an image that looks like this, you have to create some knowledge that says, I know where my neighbors are, like where are my neighboring streamlines. I can find my pre-existing and neighboring streamlines. That's kind of the essential characteristic of this. So the idea is that streamlines should not lie too close to one another. That implies that somehow they know about each other and are aware of each other. That's the essential knowledge that we're bringing in. So the main steps are to choose a seed point with distance d separation from an already existing streamline. That's the knowledge right there. So we're choosing streamline seeding points based on pre-existing streamlines. Then we do forward and backward integration for a certain amount of steps. And again, it's until the distance d test is reached. That d test is the distance between the current streamline and the existing streamline, so we don't collide into them. We don't overlap. And there are two parameters, two very important parameters, d-separation and d-test. So let's look at this slide first, actually. So there's a streamline in the middle that is thicker than all the other ones. I don't have a laser pointer, right? We could have a laser pointer or something like that, or an old-fashioned ruler. There's a streamline in the middle that's thicker than the other ones. Everybody see that? You can imagine that that is your first streamline. So the first step of the algorithm is choose any point, any seed point, and trace a streamline. So that's the first thick one in the middle. And then we can choose a spot along the streamline, like right there, and we can search on both sides for empty space. And if we find empty space, like here, for example, we can see the next streamline. And that distance, d, is d-sep, the separating distance between the current streamline and the next streamline. Then we forward integrate and backward integrate, starting with this seed point, and we add that streamline to a queue, a list of streamlines to be processed. And then we return to the one we were working on, that we were searching here, and we keep searching for more empty white space to plant new seeds. We don't find any white space here because it's occupied by a streamline, but then we get to a certain distance, like here, and we find there's an empty space where we can seed a new streamline. So we backward integrate and forward integrate until we hit the edge of the boundary, as you can see. And then we add that streamline to the same queue that I just mentioned, the same queue that this one got added, the future processing queue, or the future search queue. And then we repeat. So this is a while loop. We go back to our original streamline and we keep searching. So we're traversing the streamline and we're searching on both sides for empty white space. And the third one is here, right? That's the next time we find some white space. So that's our third streamline seeding point. We forward integrate, backward integrate, and enter that third streamline into the queue, the future processing queue, and repeat. Does that make any sense? So essentially we are searching this white space. This is a 2D plane. We are searching this 2D plane for empty white space, but we're not searching it in the traditional way. We're searching it based on streamlines. It's like, here's a streamline. Let's start searching the empty white space along this streamline for seeding points, for seeding candidate regions. So we would trace this initial streamline, then start searching on to the left and right for seeding positions, until we finished, we got to the end. And once we've processed this streamline, in other words, once we've searched the space on either side of this streamline, it's done. Like that streamline is done. It's taken out of the queue and it's processed. The next one is this one. We take this one out of the queue and we perform the same search. It's not shown here, but if we took this one out of the queue and started searching, we would find an empty space here and seed a new streamline there. And we would forward and backward integrate it and add it to the queue. And we keep going when we search along here for all the empty spaces and seed points. So we would have, that's the second one, so to speak, and then we would take the next one out of the queue, which is this one, and we would search both sides, and so on. So this is the pseudocode. This is what the algorithm actually looks like in kind of processing logic. So we compute an initial streamline and put it into a queue. That was that thick one in the center and that slide. And then we set that to be our current streamline. And there's a while loop here, while not finished. Well, not finished is like on the next slide partially. We search both sides of the stream. We searched both sides of the current streamline for a seed point which is d-sep away from the current streamline, so an empty space, d-sep away. If we find an empty space, then we plant a seed and use that to compute a new streamline and put it in the queue. Otherwise, if there are no more streamlines in the queue, then we're finished. Right? Otherwise, we take the next streamline in the queue, and it becomes the current streamline until there are no more streamlines to process or no more streamlines to search. The terminating conditions, when to stop streamline integration. That means when do you stop or terminate a streamline, stop trying to trace it through the flow. When the distance to a neighboring streamline is less than or equal to d tests. So whenever we're tracing, we're testing to see, is there another streamline in the neighborhood? Are we going to crash? Are we going to collide with another streamline? Are we within d tests of a distance? If so, we terminate. We also terminate when the streamline hits the border, the boundary of the data. It's also terminated when we hit a critical point. That's an area in the vector field where the velocity is 0. That's called a sink. That's a sink, and we saw an example of that last Monday in that nice little animation of the streamline integration. We also terminate a streamline when it overlaps with itself, so that can happen. They form loops that overlap with themselves. Or after a certain number of maximum steps. That's to catch these weird streamlines that spiral in a very, very gradual way. Like you can have a streamline that forms a spiral, and the spiral is so fine that it almost never ends. It takes too much computation time away from the user. So the two magic parameters are d-sep and d-test. No pun intended. This is what happens when you set d-sep to 6% of the image space. So you just measure 6% of the image space, the distance, and that results in separation distances that are kind of large and sparse, creates a sparse image. This is with 3%, and this is with 1.5% image space, so you can get varying density of your streamlines. Now, the d-test parameter, this is like some variations of d-test. That's the distance that you test in order not to overlap with currently or previously existing streamlines. And the higher the value of d-test is, the more you get these short streamlines, which are not very nice. That's like almost like approximating a glyph and arrow d-test. So that's d-test being 90% of d-sep. They're not the same value. So d-test is a fraction of d-step. In this case, it's half. So when d-test is half of d-step, you get a much more visually coherent result. But the spacing also varies more. But it's still a lot nicer. We can add some enhancements to the streamlines. For example, thickness. Here, the streamlines are of uniform thickness. But here, the thickness is changing. Can everybody see that the thickness is getting less near the ends of the curves? That's called tapering. Has anybody ever seen that before? That's something you would see in paintings. It's like an artistic style. Something you would see in drawings and paintings. Is the attendance register somewhere? It's ended up in a random spot. Everybody sign it? Everybody sign it? Okay, that's good. And these are glyphs that are added to show the downstream direction. See, these don't show downstream direction. You don't know which way is up and down, so to speak. So we can add glyphs that show the downstream direction. And that's if somehow you got lost in that explanation, you can read the paper. It's on Blackboard. It's a fun flow visualization algorithm, and it has been on previous tests. And now we look at the video again. When I first gave that lecture, that algorithm is for 2D flow, planar flow. When I first gave that lecture, there was no algorithm like that for flow on surfaces. So we wanted to extend that algorithm to surfaces, flow on surfaces. So this is the evenly spaced streamline algorithm for surfaces. We're not going to get into the details of it, but this is what the algorithm looks like in action. But now you can get the basic idea. So this is the evenly spaced streamline algorithm. It's no longer confined to 2D planes, but it's on surfaces in 3D. And they're showing the properties of the flow just underneath those surfaces. And it's just nice to see what the algorithms look like when they're alive and applied to real data. And it's also interactive, so you can interact with the different things. Now, to get it to work on surfaces, it had to be modified, right? We had to add this edge detection, so streamlines were not just traced across edges. We also added this animation that shows the downstream effect, you know, to clearly make it looking like downstream and upstream directions. We added tapering again, so this is similar to the first one. Now that grid, that's showing the underlying grid that stores the data. You can see that that grid is complicated. This is one of the reasons why nobody had done it prior, because that grid, it's not just a Cartesian grid, like in the 2D, so it's very complicated. This is the user interactively adjusting d-sep, so to get varying densities. In this version, there are two kinds of seed points, that as opposed to just one kind, as in the previous version, but we won't get into the details. Again, you can see the underlying mesh. We also add the perspective foreshortening. This is with no perspective foreshortening, so it's evenly spaced, and the depth, how far away you are from the camera, is ignored. Doesn't matter. Now this one, the spacing changes if you're far away from the camera. So here the space is larger, and there the space is smaller. Everybody recognize the cooling jacket? So that was done by Ben Spencer. Very talented individual. Okay, are there any questions about the evenly spaced streamlined seating algorithm? Does anybody think they could answer a test question on that, for example, or implement it? In some database classes, that is a coursework to implement the evenly spaced streamlined seating algorithm. But let's have a quick preview of the next one, if you want to know what's coming up. In the next one, we're going to talk about stream ribbons and stream tubes, seating dimensionality, and stream surfaces. So stream surfaces, and I think, are we going to talk about path surfaces? Path surfaces is there, but we don't, it's not really much different. Oh, and then streak surfaces. So it's really, the complexity increases in the next ones. Any questions? I think that would be a good place to stop then, if there are no questions.